Hi everybody, I'm going to be talking about your online experiment. For some of y'all this is experiment number 4, for some of y'all is online experiment number 5. But really what matters is what this experiment is all about. This is an experiment all about enthalpy of reaction. So one way that you could think about this is what is the heat that is produced by this reaction or by a reaction? So in our scenario, we've got a pair of substances. We've got reactant X and reactant Y. And what we want to do is we want to mix these two together and see ultimately what's produced. Now, unlike in reactions where we're talking about, or unlike in scenarios where we're talking about balancing a chemical reaction and we're looking at an actual product, what product we're looking at is the generation of heat. Okay, so on this, if you look, there's a little bit of a scenario that's described where somebody's heating or where somebody's camping and they're trying to cook food and they mix these two reactants with one another and they're going to generate heat. We're kind of we're moving away from that. And what we're trying to do is we're trying to figure out what is the perfect ratio of reactant X to Y. Okay, now we don't have a balanced chemical reaction, and arguably we don't really care too much about that, because the way that we want to look at it is we want to perfectly match up the amount of X and the amount of Y to maximize the amount of heat that can possibly be produced. Okay, so your data sheet on this has you going through, or I'm sorry, the procedure here has you going through a number of different trials. So we'll say trial number 1. Trial number 1 has you mix X and Y. I'm going to scribble that out and I'm going to rewrite it. So T1, and I'm going to put X, Y, and heat, or temperature, I suppose. For trial number 1, what you're going to do is you're going to mix a total of 10 milliliters of reagent X and 40 milliliters of reagent Y. Okay, for trial number 2, what you're going to do is you're going to be mixing 15 milliliters of X and 35 milliliters of Y. Okay, now, and you'll go through a total of 4 trials that are described, and then you'll have to come up with your additional 4 trials to actually produce. And you'll be coming up with a graph for this, so just bear that in mind. Now, one important thing that you should take away from this right here is you have a fixed volume. We have a fixed volume. I'm going to write this out. We have a fixed total volume and fixed concentrations of solutions X and Y. This is important because by maintaining a constant or a fixed total volume and maintaining fixed concentrations of our 2 different solutions, when we change from trial 1 to trial 2, when we go from 10 milliliters of X to 15 milliliters of X, and correspondingly 40 milliliters of Y to 35 milliliters of Y, by changing the volume of each individual reactant, we're effectively changing the number of moles. So if you think about this as 10 milliliters, sorry, I'm running out of space here a little bit, 10 milliliters, also known as 0.01 liters of X, with a solution that has a concentration of 0.1 molar, well then we're working with, let's see, that's 0.01 times 0.1, that would be 1 times 10 to the negative third moles of X. Okay, so then for trial number 2, so that's what it would be like if we're looking at 1.10 to the minus third, 15 milliliters, we've got 0.015 liters, and that 0.015 times 0.1. We've got 1.5 mils. I'm going to scribble this out. We have 1.5 times 10 to the minus third moles of X. So we keep this constant volume, but we're changing, or we keep the total volume constant, but we're changing the individual volumes of reactant X and reactant Y so that we can vary the number of moles. And so what we're doing is we're basically playing with this ratio and trying to come up with a balanced chemical reaction, or we're trying to optimize our two reactants so that we generate the most of our product possible. All right, so I'm going to walk you through kind of the procedure for that in just a moment, and then I'll be back. Well, yeah, I'll be back whenever I'm walking through the procedure. All right, so here we are. I'm going to go ahead and help you all out with a little bit of the procedure and talk to you a little bit about what's going on there. Okay, so so here we go. This is what your workbench looks like, and what you're going to do is you're going to get a piece of glassware, and there's a couple of things that we want to look at here. We've got a, I'm just going to do this as a comparison. This isn't exactly a part of your procedure, but I'm going to get a foam cup and I'm going to get a 250 ml beaker. Okay, and we're going to do a little bit of a comparison here. Then we're going to get our 0.1 molar reagent X solution. We're going to get 0.1 molar reagent Y. I'm going to add, let's go with 25 mils of reagent Y to my 250 ml beaker. Done, it's in there, great. And as you can see, it's about 25 degrees. There it tells me the concentration of hydrogen ions and hydroxide ions, as well as my species, my soluble, my aqueous species Y. Now I'm going to add reagent X. Okay, again, 25 milliliters just to make it completely equal. And lo and behold, it got to 27.3 degrees, and oh, it's dropping quite fast. Okay, let's think about this. This is a piece of glassware. This is a glass beaker. That glass beaker is susceptible to the environment. And so we're going to see that temperature hit the top and then drop very, very quickly. Now let's compare that to our foam cup. Okay, 25 milliliters. Pour. Okay, I just put X in there, and I'm 25 milliliters of Y. And boom, 27.3 degrees, and it holds. That's an important part of this. That piece of instrumentation is known as a calorimeter. So you're able to actually watch the heat of that specific reaction. Now, yes, it is a styrofoam cup. It is a foam cup, but it's effective because whenever you're drinking coffee from a styrofoam cup or something like that, it's insulated from the environment. So any sort of draft of air that blows past it, it's not going to cause the solution to go up, or sorry, it's not going to cause the solution to drop very quickly. So that's a very important detail of this experiment. Now, with that said, I can clear my workbench. I'm going to go ahead and add, well, I'm just going to add 2 of them. I'll remove this third one. So I've got foam cup. I'm going to go back, get my solutions, Y and X. Okay, so I'm going to start out by doing the very first trial. I'm going to add 10 milliliters of reagent X. And I've done that. And now I'm going to add 40 milliliters of reagent Y, 25.92. So I'm going to write that down on my my worksheet, or my data sheet, 25.92. So that's a temperature change of 0.9 degrees. Okay, now let's go to the next one. Reagent X, I've got 15 milliliters of reagent X, and to that I'm going to add, well, 35 milliliters of reagent Y. Okay, so that gets me all the way up to 50 milliliters. So now I've got foam cup 1 and foam cup 2. They're not labeled, but my foam cup on the left-hand side is at 25.9 degrees Celsius, and the foam cup on the right is 26.4 degrees Celsius. Now, let's think about what's in these two. Okay, so I'm going to write them out. So, oh, I suppose I have to use my actual tablet for writing rather than a piece of paper. 10 mils of X and 40 mils of Y, 15 mils of X, and 35 mils of Y. Okay. Now, what this shows you is that if we're increasing our amount of X and decreasing our amount of Y, well, our temperature goes up. At some point, like let's think to a very extreme. With the logic from these two data points, we would believe that if you put 49 milliliters of X and 1 milliliter of Y, then your temperature would arguably or potentially be the highest. You know, let's say that our temperature got to 60 degrees Celsius. Okay. Now, that's a conclusion drawn on two pieces of data, two data points. And to say the least, that's kind of a flawed and failed conclusion. We know that it's ultimately a ratio that we need. It's a specific ratio where we're going to have reagents X and Y in perfect balance with one another. So what we want to do is keep going through. Your data sheet shows you adding a total of 4 different trials by increasing the amount of X and decreasing the amount of Y by 5 milliliters at a time. After you've done that, you'll need to plot that data and see what that looks like. Now, in the event that and I'm going to clear these writings, in the event that your data looks like, I'm going to try to draw this as well as possible. If your data, that's not a very straight line. If your data looks a little bit like this. Oh, sorry, my y-axis is going to be max temp. Now my y-axis is going to be actually twofold. It's going to have 2 parts. So the first data point is 10 mils of X and 40 mils of Y. The next data point is 15 X and 35 Y. 20 mils of X and 30 mils of Y. 25 mils of X and 25 mils of Y. Okay, so sorry about that. With this data right here, with this very small and narrow sample size, we don't really know where it's going to go. This data could go like this. It could go like this. It could continue in that trajectory. Alternatively, maybe what happens is we reach a point where we've added more than enough of reactant Y, or I'm sorry, of reactant X, and the data actually begins to decline. Okay, so if in the event that it begins to decline, you'll have to make your decision. What is the combination of solutions that you would need to use to reach the maximum temperature? Okay, so I'm going to go ahead and remove these last 2. If you get a graph that looks like that from your first 4 data points, well then I think it only makes sense to use another data point that is 30 mils of X and 20 mils of Y. Because if that data point goes here, or if it goes here, you're going to learn something about the maximum or the optimal balance and the optimal ratio. If it goes like this, so we scribble this one out. If the data goes up and then it begins to go down, maybe that 25 and 25 is the perfect ratio, but maybe if you put 27 mils of X and 23 of Y, maybe that would be the perfect ratio. So basically what you're going to be left to determine is, based on the data that you're presented with, what other data points do you need to come up with? So you're going to have the chance to come up with 4 original kind of combinations. And you'll base that on the direction of your data. Now, like I said, if the data if the 30 milliliters of X and 20 milliliters of Y does this, well, then my first thought is I have it increasing until I get to 25 milliliters, but then I see that the maximum temperature goes down once I hit 30 milliliters. I should probably test data points here, here, and here. So basically between these two data points. And if you do that, you're kind of fine-tuning to figure out what is the optimal and what is the maximum temperature that you can possibly observe. Okay, so that's all there is to this experiment and to this sort of exercise. You'll have to do a total of 8 trials. 4 of them are prescribed. 4 more of them you'll have to determine yourself. So that's basically the gist of this. I'll be back in just a moment to go over some more details of the concepts and what you can do with this sort of information. All right, thanks. All right, so I'm back, and that's basically what you're going to be doing for this experiment. You're going to be doing a number of different trials, and you're trying to figure out what the perfect ratio of these two systems, or what these two reactions are. Now, how is this valuable? Well, one way that it's valuable is you're learning a lot about enthalpy, and you're learning a lot about basically the heating of a system. So we have reactant X and Y that what they are doing is they are reacting with one another and they are heating up a solution, and that solution is a water-based solution. Now that water-based solution, well, that has a density of approximately 1 gram per milliliter because it's based in water, and it might be a little bit more than that. It might be 1.1 or something like that, but we're looking at it kind of as a negligible amount. Now, with that to consider, what we're seeing is the change in temperature of water. And we're seeing that change in temperature because we're using, like, our reaction tells us the thermal properties of a given, our workbench shows us the thermal properties of a reaction, but we're monitoring the change in temperature of water. So what we can do is we can use the equation Q equals mc delta T. And what this tells us is the heat of a reaction. Okay, so how much heat and the units here are important. They'll be measured in joules or kilojoules. Now, this equation right here, the way that you can kind of unpack it is M stands for mass. The mass of a substance that is, well, experiencing some heat and changing. C is something known as the heat capacity. And delta T is going to be, well, this one's kind of self-explanatory, change in temperature. Now, the way that we can use this equation is we can kind of figure out for our different reactions there, we can look at our specific heat capacity of water. Let me go ahead and change that, specific, of 4.18 joules per gram degrees Celsius. Now what that tells us is the amount of energy that is required to change 1 gram of a substance 1 degree Celsius. Okay, so let's go ahead and set this equation up to solve for Q of trial number 1. Okay, now if I remember my trial number 1, it got to, and I'm looking at I'm alt tabbing right now. My trial 1 went from 25 to 25.9 degrees Celsius. So I have a delta T of 0.9 degrees Celsius. Okay. Now my M. Okay, so M is a little bit complicated because you might be thinking, well, is it the mass of reactant X and reactant Y? I don't know, that's kind of tricky. The answer for this is, what is the substance that you're observing change in temperature? What we're observing is we're observing the water. Our solution is changing temperature. So our M is going to be the mass of our solution. Now, we had a fixed volume of 50 milliliters, and we can use the density of water to figure out the mass. So we had 50 milliliters of solution. Now, the density of water is 1 gram per milliliter. We're going to use that as our density of our solution. If we have 50 milliliters of our solution, that means we have 50 grams of our solution. Okay? So we've got those two variables. We've got M and delta T. The last one is our specific heat capacity, C, which is 4.18 joules per gram degree Celsius. Okay, so to figure out Q, that's going to be, well, 50 times 4.18 times 0.9, which is equal to, I've got my calculator right here, 50 times 4.18 times 0.9 equals 188.1. My units here are joules. Now, what's important to think about here is, and when you think about heat, you should be thinking about it in terms of transfer. The heat is being produced by one thing and then being absorbed by another thing. Well, what is changing temperature? Or what are we observing change temperature? We're observing our solution, our water-based solution, change temperature. So what that means is the water is absorbing heat. So if the water or our solution is absorbing heat, that means our reactants at the molecular level, those are producing heat. So what we'd want to say is X and Y, and sorry, one of the ways that we can put this is X and Y produce an exothermic reaction. And so what we could say is the heat that is produced by X and Y, Q, is equal to negative 188.1 joules. That heat is absorbed by the water, which is why we see the temperature change. Okay, so really the purpose of what I wanted to get at here was, what are we watching change? We're watching the change of our solution, or we're watching our solution change temperature. And we're watching that because we have reactant X and reactant Y, well, that are producing heat that is being released from it, and then the water is absorbing it. And so we're observing water's temperature change for the we're observing water's temperature change. That's what we're doing. Oh, sorry. Okay. I hope this was helpful. I hope this helps you along the lines of doing your experiment. It's one of the trickier parts about this is labeling your axes. Keep in mind, what is the composition of each one of your trials? Trial 1 is 10 milliliters of reactant X and 40 milliliters of reactant Y. Trial 2. So putting that on the labels for your graph is one of the parts that's a little bit tricky, which is why I've recommended that you graph with graphing paper. There's a link within the experiment where you can download that graphing paper, print it up very easily. When I was in elementary school, we always had to have graphing paper, but I don't think we ever really used it. Now, you can just print it up. So now you don't have to go buy graphing paper or anything like that. All right, well, I hope this is helpful, and Have a good afternoon, everybody.